Hello, my name is Jeremy Byrne. I'm loading Softimage version 3.7 today, running on a Silicon Graphics workstation. The look of the user interface will differ slightly if you're using the Windows NT version of Softimage. When starting to model in Softimage, one of the first decisions you have to make is to choose a type of geometry. As a broad category, Softimage uses the term surface to include all patches and NURBs. Through the next sections, we will compare and contrast these surface geometry types to polygon meshes. Polygon meshes are loosely structured and can be put together in many different ways. A primitive sphere made out of polygons consists of mostly four-sided polygons with poles at the top and bottom. A primitive dodecahedron doesn't have any poles and consists purely of five-sided polygons. We can modify the structure as we model to add details to parts of the mesh. The ability to add points exactly where we want them is a major advantage to polygon meshes over surface objects. In polygon edge mode, we can add edges connecting the new points and then move a point to add a local detail. We can also tag several vertices at once and add more points to the entire tagged area while we're in tag mode by selecting Effect Rounding. Effect Rounding can give one specific subregion of the mesh a higher resolution than the rest of the object, and can create much denser subregions if the command is used more than once. Surface objects have a more fixed structure. The geometry is a grid with four sides. The rows of points running in the U direction, shown with the green edge flag, intersect the rows of points running in the V direction, shown with the red edge flag. Each interior point is always connected to exactly four other points. To preserve this structure, trying to add a point to one part of the surface will always add a whole row of points extending all the way across the model. So we have to add details to surfaces very selectively, because too many of these unwanted rows of points can use up available memory and make the surface difficult to sculpt and animate. A single surface object that forms a sphere will always have poles on both ends because the sphere is still a rectangular grid in structure. Only two things have happened to it. First, it's been closed in the U direction, and second, it's been capped in the V direction. One step at a time, just to make a surface that's closed in the U direction, we can revolve a spline, swept 360 degrees. Now the U direction lines of our grid are closed circles. The red edge flag shows the seam where the opposite edges of the surface meet. Since modeling relations were turned on, I can still change the shape of the surface by editing my original curve, and the remaining opened edges can be dragged to the center axis, creating a pole at the top of our model. The top edge of this surface still has just as many points going around it as before, even though these points are all drawn together into the same position in space. To ensure that the pole will stay together throughout editing and animation, we could turn on capping under Info Selection for this model. But this model is still only closed in the U direction. If we took the cross-section curve that we're revolving and closed that curve, then we would produce an object that is topologically a torus or donut shape. Only these donut surfaces are closed in both U and V. Unlike polygon meshes, patch and NURB surfaces can have curved lines between each control point. The curves themselves are actually made of a finite number of straight line segments because surfaces are actually subdivided into flat polygons when they're rendered. In Info Selection, if the number of subdivision steps were turned down to 1 in both the U and V directions, then we would be back to straight edges between each control point, even with this B-spline patch. Setting them both to 2, we can visibly see the two line segments making up a crude approximation of the curve. On 3s, which is the default setting for primitives, we are back to a smooth-looking curve, but could still see faceting in places where the geometry were pulled into a tighter bend. We could raise the U direction step to 6, but lower the V to 2, so then we'd have a smooth-looking curve in our shot, while still saving polygons that would only be visible from other angles. Above these step values, the curve settings only affect the wireframe display you see in the viewport, not the shading or rendering of the object. We can set our curves to 3 and 3, matching a 3 by 3 step subdivision for the surface. Now the wireframe shows us the exact location of the surface's subdivisions. But here's something to watch out for. If we set them both to 4 by 2, we can see that they don't match up anymore. An unfortunate feature of this window is that the U and V values seem to have been switched between these settings. To fix this, always put the U step value into the V curve value and vice versa if you want to see them match. To adjust the curvature of several objects at once, I can multi-select all of them and then choose Info Mental Ray. The selection size here is 3 surfaces, whereas Info Selection would only operate on 1 at a time. There's 2 steps to using this dialog box. First, choose Select Unselect Propagated Fields and click on the attributes you want to adjust. Second, switch to Edit Field Values and modify the selected settings. Now when you click Apply Unselected, the settings you have chosen are applied to all of the selected surfaces at once. The different types of curves each have their own advantages. Cardinal splines always run directly through their control points, making them useful as animation paths. B-spline curves can roll right past their control points without touching, but are more consistently smooth curves without risking the kinks that can sometimes develop in cardinals. Linear splines are just straight edges by themselves, but can become more useful when combined with another curve type within the same patch. For example, I could start with a Bezier curve, which gives us a very controllable curve with handles, and I could draw a cross-section for a box I want to build. But when I use the surface revolution function, I'll choose linear splines in the V direction with 4 sides to make a box. This makes an effective box, although for high-quality renderings you may wish to avoid these razor-sharp edges. A better way could be to use B-splines and an 8-sided revolve. Of course, the initial result is round, so we have to tag half of the points and double them up to make corners by rotating 45 degrees. Now we're back to a box shape, but with smooth B-spline bevels. This patch still has a Bezier cross-section in V, but is B-spline in U. We'd use other options to build the box out of NURBS. We could draw a cross-section using quadratic NURBS. If you select a quadratic point and adjust its weight as close as possible to 0, then the adjacent points will form sharp angles. We can revolve our quadratic using cubic NURBS in the V direction. Now with NURBS, you don't need to double up points to tighten the corner, you can just adjust their weight. We can adjust the weight higher to draw the surface to meet our tagged points, or lower the weight to give them less influence so the surface comes closer to passing through the untagged points. So, when should you use patches and when should you use NURBS? As we've seen, NURBS control points can be weighted, giving more control over the surface. Patches, on the other hand, can include Bezier curves in one direction with weightable handles. With NURBS, you're not required to have the same number of points in all the curves used in a surface scan or draw merge surfaces command as with patches. NURBS also avoid the problem we can see in this B-spline patch of distorting its shape as new points are added to the surface. NURBS surfaces can be trimmed. Note that trimming still leaves all the same control points on the surface, even though a portion of the surface is hidden by the trim. Trimming a surface can actually produce more geometry once the surface is subdivided. We can see this by trimming one copy of a surface and converting the trimmed and untrimmed copies to polygons. As polygon meshes, we can see all the extra work that Softimage is doing to represent the trim. Info Selection will confirm that more geometry actually exists in the trimmed model. Patches can be seamlessly fitted together with zipping operations. NURBS have a surface blending function, another way of fitting together surfaces. We'll talk more about both later. It's easy to convert a patch to a NURBS surface with the effect convert command. Converting a NURBS surface to a patch would be much slower, because first you have to extract all the cross-sections, then you have to convert all the extracted NURBS curves to B-spline curves, then you have to skin all the curves together into a patch. This means that starting with a patch is a safer choice if you might change your mind later. The great thing about faces is how easy they are to create. Take any curve and in one convert to face command, you have a renderable face. One more command, attach hole, and you have a hole in your face based on any other curve. It's a quick way to start an extrusion and make an object with a hole in it. Faces are also a quick way to build a cap for an open surface by just extracting a curve from the surface and saying convert to face for that curve. The bad news is that faces are only made to work when they remain flat. If we try to deform one, as I'm doing with this lattice, it can break up and show visible glitches. Faces also differ from surfaces in that they don't have UV coordinates for attaching texture maps. Often we're better off building a surface based on our curve than converting a curve to a face. So if we extract this curve again, we can make a second copy of it and scale the second copy down to a size of 0, so it's all at one point in space. Now we just skin the 0-sized copy to the extracted curve, and we've built a fully deformable surface out of our curve. Unlike a face, our new surface can be merged with the original NURBS object, producing one continuous deformable model. The skinning technique will also work to replace some faces with one hole attached by skinning the outer curve together with the hole. But if we had a more complex curve shape, or more than one hole, we would need another technique. Any face based on NURBS curves can be replaced by a trimmed NURBS surface if we just get a primitive NURBS grid and scale it to a size that will include our curves. Now we'd select Draw Trim NURBS Surface, pick the outer curve, and use the crop operation. Instead of attaching holes, we'd just use Draw Trim NURBS Surface again, pick the hole curves, and use the remove operation. This gives us a true surface that's fully deformable and mappable. Softimage's metaclay can be an easy way to block out organic forms in 3D space. We can just add a metaclay element to the scene, then hold down the D key and click to duplicate it to make more elements in the same system, and then drag copies into new positions, scale them, rotate them, or translate them to add to the overall shape of the metaclay system. If we get info selection for an individual meta-element, the meta-element info box will let us change the shape of an element. By setting the x, y, and z superquadratic exponents to 8, we get a rounded box shape, which still melts smoothly with the other metaclay elements. Negatively weighted meta-elements will make dents or cut holes in your metaclay system. An unfortunate feature of this window, however, is that it throws away negative values and replaces them with positive ones. To override this feature, we need to write an expression for the meta-element, which sets the element's clay weight equal to the constant value -2. This refreshes the value back to -2 at every frame, so we can now use our meta-element with a negative weight. As with NURBS and patches, metaclay gets subdivided into a finite number of flat polygons for shading and rendering. In the system setup, a smaller rendering slice size will subdivide the metaclay system into smaller slices, creating more refinement, but of course more polygons. Metaclay systems differ from surfaces, however, in not being texturable with a map that will stick to the surface during animation. Because of this, we often need to build a surface based on the metaclay system before animating. Converting a metaclay system to polygons is easy. You just say convert to polygon. Note that this polygon object is a lower resolution than the metaclay system. This is because conversion to polygons is done based on the wireframe slice size, which can be independently adjusted. If the wireframe slice size were the same, the polygon mesh would look identical to the original metaclay. Now, to convert a polygon mesh to a surface, we'll use the shrink wrap function to wrap a B-spline surface around the polygon mesh. Shrink wrap requires 3 objects. First, an outer wrapper model, which can be built as a revolved surface around the form we want to shrink wrap. It has to have enough points to approximate the surface it's wrapping. Next, an inner wrapper model, which is usually just a copy of the outer wrapper model. Every point of the outer wrapper model will travel towards the corresponding point on the inner wrapper model, stopping only when it intersects with the polygon mesh. We're prompted to select the target mesh, our outer wrapper model, and our inner wrapper model. Our result will be a new B-spline surface based on the form we originally sculpted in Metaclay. One of the most powerful and fun modeling modes in Softimage is proportional modeling. It gives us the ability to apply sophisticated organic deformations and edit a surface or mesh by transforming as few as one point. Proportional modeling is turned on automatically when we choose proportional setup. We can make other points within 5 units follow along with the point we translate. With the linear fall-off, the influence falls off in a straight line, creating an angular cone when we drag these points upwards. The exponential 1 preset gives us a more rapid fall-off, creating a sharp spike. The exponential 2 gives us a more smooth organic results, looking similar to a bell curve. Rotating or scaling one or more points can also be used to deform the surface. One way to control the influence of the effect is by limiting it to a specified distance in space. We can measure the area we're looking at with info distance and then use this distance as a distance limit in the proportional setup box. Another option, which is available on surfaces but not for polygon meshes, is checking the surface box to limit the influence by a number of coordinates in u and v. This way we could adjust it to primarily affect one row running along the model in the u direction only. We can limit proportional modeling to only move points that we've tagged with the Effect Tag Only option. Of course, this limits us to moving points one at a time with the M key. We can't tag the points we want to move when our tags are being used to limit the effect. A more powerful approach to locking off points is to tag the points you want frozen and define a new cluster. You can give it any name, and with that cluster still active, go to the Motion module and Shape Save Cluster key. Now you can edit the surface, and the frozen points will always refresh back to their saved positions when you go to a frame or press the R key. The freezing effect will continue until you reset the cluster animation. The Consider Neighborhood option means that only points that are connected to the ones you're moving will be affected. For example, if we were moving points in this face with an attached hole, by default we influence all the points within the distance limit. With Consider Neighborhood, moving a point on the edge of the face will not move points in the hole, and moving points in the hole will not affect the rest of the face. Once in a while, you run into a situation where multiple models have been merged together into one polygon mesh. This can also happen when importing from other file formats. If this is now all one object, separating overlapping pieces can be very difficult. Consider Neighborhood gives us an easy solution. If we turn up the distance limit to a very high number, we can simply drag one point to pull out all the connected polygons, almost as though we were translating an object. Then we could make multiple copies of the merged model and use this technique to pull out and delete different portions from each copy. Proportional modeling isn't just for freeform work. If we want to model a screw, we could start with a simple extrusion, then tag the bottom row, and just rotate around Y until we had enough of a twist. To make a point, we could give ourselves a sharper fall-off for a tapered head, and then scale to 0 in X and Z, but not the height, to make a point. For many models, your design process will begin outside of the computer with drawings, clay models, or researched photographs of a real subject. You can put these images into a rotoscope wire window and draw curves to outline them. Once you've got key contours from 2 or 3 angles, you can position them in space as a 3D reference. For a human head, often the most important curve is the profile, which defines many of the key proportions. Then your second curve can be an edge defining the sides of the head. Don't make this too big, since you're modeling just the head itself without hair yet. Good visual reference is very important in getting these curves right. Next, we need to fill in the space between these curves. With our radial cross sections, we'll be able to skin together. The curve next to the profile will not have the nose sticking out as far, so we can make a copy of the profile and move points, but not delete them, to get rid of the nose and start into some eye sockets. The mouth will be tapering off by now too, and we can rotate our modified curve a little ways around the central axis. We continue around making copies of the curves, rotating and modifying them. The goal at this stage isn't perfection. This is just getting us a better starting point than a primitive sphere. Just get the curves about where you want them, because we will have to add more curves and tweak the shape afterwards anyway. You can choose to draw a few more or less curves than this, but when you want to make a surface, just skin the curves together, and we've got a good start to our model. From this framework, a process that can take several times longer than the original skinning operation begins, a process of adding edges and dragging points, often in proportional modeling mode, will move us towards a more complete surface. I started the last head with a pole at the top, but other parameterizations are possible. Mouth-centered models are just as good for many designs, like this character. Here, one pole is at the center of the mouth, so each curve radiates out of the mouth, then bends down to the open end at the neck. This arrangement gives a lot of easy-to-manipulate points around the mouth, although it would not easily support high levels of detail around the eyes and forehead. So it's perfect for many cartoonish characters, and also for most creatures and animals. If we're modeling around the mouth, we position our radial cross-sections differently, but can otherwise use the same process as before. We modify and rotate each copy, then skin them together for one half of the head, which is basically symmetrical. After we get one half of the head about right, we say affect symmetry, reflecting a copy over the x-axis. Before we can merge the two halves, we also make sure to delete all of the points that would be redundant between them, so they don't bunch up. Then we draw merge surfaces to unify them. If the result comes out backwards, then we'd need to go into Effect Curve Control and reverse both the U and V directions before trying again. After you merge the surfaces, the same effect curve controls can be used again to close the head. In most characters, the neck is very visible and deforms a lot, so a blend on the neck would probably hurt the quality of your rendering. If we made a body with a similar opening, using the same number of points around if it's a patch, then we can draw merge surfaces between the head and the body, making a smooth, continuous surface. It's very rare that you should ever need any kind of a blend at a character's neck, since it's usually much easier to just make the head and body the same surface. Setting the camera's clipping plane closer can hide the backside of a surface to help us see what we're doing. Now, features such as eyes, nostrils, and sometimes mouths when they aren't at a pole in the geometry are very hard to draw into cross-sections and are usually best modeled by plain old-fashioned point dragging. You might need to add a point or two to start with so you have enough to define your form. Usually you need at least two going inside a feature, and then you need to drag surrounding points outwards to correct the surface around the hole. Don't use any more points than you have to here, because the areas where they all come together, such as the corners of the mouth or eyes, can be very difficult to control. Also, on a more complex model, inserting edges where you want them can sometimes mess up another part of the model. For example, if we're pretty far along in building a B-spline head and need more points in order to make nostrils, then that adds extra rows of points running across the cheek. We could manually drag the new points to smooth that area out again, but the dense area would still make editing the shape of the cheek very difficult, as well as possibly distorting the texture. So I'm going to undo a few steps here and try it another way. By the way, I'm using window D as a perspective window while I model. This way, after we inspected a model change, we're still able to undo it without having to undo through all the camera angles as we would have had to in window B. So to add points with a little bit more control, I'm going to use a cut and remerge technique. First, I'm going to cut the surface to isolate the area where I need the points. I'll hide the original model. Now we can add points to the nose. Of course, the remerged result will need to have the same number of points added all the way around, but we can add those wherever we want to the other section of the head. There's room for them down lower where it looks like they'll do the least damage. Now I want to remerge the surfaces, but first I'll delete this edge so they don't hit each other, and then I'll select Draw Merge Surfaces. The two surfaces will fit together very well since they were unified before. Now I can use my precious extra points to define the nostrils. To better inspect the work you do near the center of the face, we can select the half head and use effect symmetry to reflect it over the x-axis. Some people find it distracting to deal primarily with half a head at a time, but for detailed models where you could spend an hour dragging points for a single feature, the potential time savings is hard to pass up. Compared to patches, NURBS have made two small steps forward in detail management. First, adding points to NURB surfaces does not distort the shape of the surface. Even though whole rows of points still need to be added where you only wanted one, at least the surface is not visibly distorted in the process. Second, the ability to weight NURBS points means that you can control a sharp cusp or indentation using fewer points. This sometimes allows fewer total points to be used in defining a model. In the real world, a lot of details protrude off the surface, like this polygon hair. We will use the duplicator effect to apply these hairs to a B-spline llama. Duplicator works better to a polygon mesh model, so we'll convert a copy of the head to polygons to use as input for the effect. Now in Duplicate Duplicator, we choose a number of copies and click on the base model and hair model when it prompts us to. There are other techniques for simulating surface fur that don't get drawn into your scene until you render in Mental Ray, but in terms of integration with the scene, matching the motion blur, the lighting, the shadows, and every other attribute of your surface, geometry-based details are often the best looking choice in your final render. Another way to get more protruding details onto a surface is to start by modeling a flat model of the skin and putting in all the details you want, including the pores, nostrils, and even added hairs with Duplicator parented to the main model. Now we can wrap this detailed skin around the llama's nose by creating a deformation by surface for the whole hierarchy. The scale, rotate, and translate controls can be used to position the nose detail where you want them on the nose. The underlying model will be much easier to animate than the detailed model, so if we wanted to make him sneer, for example, we would move or animate the points in the low-res model and let the deformation by surface update the detailed model to fit. Because a surface is always a grid, it has its own two-dimensional coordinate system, not measured in x and y like an image, but in u and v. We can apply texture maps based on the u-v coordinates of a surface. We call these implicit texture coordinates because they're built into the structure of the surface instead of being assigned. If we grouped several surfaces that don't have their own materials under the one we've textured, they will each inherit their parent's texture, so we can see how the same texture map follows the shape of each different object. When you're planning any surface model, try to imagine how you would bend or wrap a single piece of paper into that shape. No matter how it's stretched or twisted, it always has its top, bottom, left, and right, and still has its rule lines running in the U direction. A trim has no effect on the mapping or the parameterization, and only hides a portion of the map. This character's B-spline patch hair has been modeled to take advantage of UV mapping, with the V-direction curves following the desired flow of the hair texture. This means that a simple texture map can be applied, in which the hair moves through the map vertically, and the UV mapping will deform the texture to flow in the appropriate directions. If we hadn't planned ahead while we were modeling, these mapping results would be impossible. A similar UV mapping trick is used for the eyelashes. This time, there's an alpha channel used for the transparency in our UV map that we can have a look at in the Paint module. By making parts of the eyelash surface transparent, we create the look of separate eyelashes out of what's really a single surface. You have to plan ahead, and sometimes even do test renders early in the modeling process, to decide which details really need to be modeled and which can be created with texture mapping. The flexible structure of a polygon mesh allows a single mesh to branch into multiple forks or limbs. If we draw several spline curves, parent them together, and get a primitive circle to extrude along the hierarchy, we can use the T-branch effect. We can use the default settings. The resulting object is necessarily a polygon mesh. If a branching form like this needed to be created out of NURBS or patches, we would most likely have to build it out of more than one surface object and try to blend or fit them together so they looked like one continuous surface. With polygons, if we need to attach an arm to a body, we could start by tagging and deleting some of the polys in the body, and maybe clean up the holes by adding edges and deleting triangles. Now this edge is already tagged, and we can tag the edge of the arm and say polygon stitch. We accept the defaults and click on the left and right models. We'll need to tag and drag some of the points to clean up and smooth out the result, but acceptable looking results are possible with this old-fashioned technique. We do need one hole in the base object for each limb that gets attached. So if we start with a revolved surface for a palm, we have to draw a polygon to bridge the top to the bottom and then add some vertices and edges so we can pull it out into a curve. Now we tag the edges of the opening and tag the edges of the finger and polygon stitch the results together. We can hide the original halves and examine our completed model. A single object hand is fairly easy to assign to a skeleton. Just draw a skeleton for each finger, and then make the end effector of the hand chain the parent of the finger chains. Then in one step we say skin global envelope for this entire skeleton. Relying on polygons, while the results might not be perfect, remains the easiest and most stable way of making a texturable continuous hand in Softimage version 3.7. Also note that not every character design needs to be stitched or blended together. For example, a turtle is a first choice character to make if you want to avoid blends. Carefully placed clothing can also hide some characters' blend areas, and segmented characters such as robots or knights in armor don't need blends at all. But for most other characters, if you don't want to use polygons, you'll need to use some combination of the techniques shown in the next few sections of this tape. Let's take this B-spline surface and draw a cut to cut it into two pieces and hide the original. Now we have two different objects, but they still fit together seamlessly. But would they still fit together during animation? We can put a skeleton into them, parent the two models together, and assign them both to a global envelope. Even when they're deformed on a skeleton, the two objects will remain perfectly fitted together. So what allows this kind of relationship to be maintained? It's easier to see with a simple grid. If we cut this B-spline patch in half, we could see the phantom points sticking out from the sides of both patches. These points are the glue that holds the surfaces together. If we moved one, we'd see a slit between them, which is sometimes useful, but we get perfect continuity whenever the control points along the shared edge itself are in the same position and both sides' phantom points match the second row of control points on the adjoining surface. We could delete points from one side of them while still preserving the continuity over the rest of the surface. We could also cut one surface and drag points to split it apart. All of this will still hold together on a skeleton as long as the control points that now match each other's positions keep the same weight in the global envelope. The command draw zip surfaces is made to create this kind of relationship between surfaces, and simply automates the process that we could do manually of snapping all the rows of control points together between two surfaces. We can use this to attach surfaces whose edges or poles line up with each other. If we wanted to attach a limb to a side of the surface where there was no pole with matching points, then we could revolve a spline into a new surface with the same number of points around, and then fit the new surface around the body with a deformation by surface. Now we translate and scale it until it lines up with the position where the limb will join the body. The Y translation controls the height relative to the surface and should be tweaked so that it's just barely above the body's skin. After we freeze the deformation, we can draw zip surfaces to attach the limb to the new surface we deformed. The result of this zipping will be fairly seamless, but it would also benefit from the transparency mapping technique that we'll talk about in a few minutes. The surface blending custom effect will create a new surface that is supposed to bridge the gap between two other NURB surfaces. To use it, first we trim a hole in the side of the body and then select Surface Blending. Now we select the two objects. The two objects will each get their own side in the dialog box, and we can select whatever U or V direction curve or trim or projected curve we want to use as our blended edge for each object. Always try your blend the first time with curve fitting turned on for more efficient geometry and easier to see lines, and only turn it off if it visibly lowers the quality of the blend. Now we adjust curve shift parameters on both sides until they line up. If the blend doesn't look good the first time you try it, in this case it came out inverted, then make sure the custom effect icon is selected and say Effects Custom Edit Parameters. Now you can go back and tweak the settings until you're happy. This time I'm switching the reverse curve and in-out checkboxes. And it's looking good, so I'll say OK again. And now I'm ready to put it into a skeleton. The trick with skeletons is just to group together the rest of the character, the base surfaces, but leave the blends and blending custom effect icons ungrouped. The blending custom effect itself will be the only link between the blend surfaces and the base surfaces that we assign to the global envelope. This will update pretty well until we get to too extreme an angle for the deformation, in which case the blend edges can become visible. We've got an imperfect blend here with curve fitting turned on. Optionally, one way we improve some blends is by making the blend overlap slightly with the base surfaces. To match the blend to the arm, we make it start not at the last chord of 3, but at 2.99. Now it looks much more seamless. Unfortunately, there's no numerical position for the trim curve on the other surface. To get overlap around the trim, we have to start with two concentric curves, and use the smaller one as a trim curve as before, but then use the Project on NURB Surface function to make a projected curve from the larger one. Now we redo the blend, running to 2.99 on the arm as before, but to the curve on surface, not the trim curve, on the body. These slightly overlapped blends are especially useful with transparency mapped edges. Another solution, in which all parts of a surface can be assigned to one editable global envelope, is to fillet together the arm with the body. We can start by extracting a curve from the arm, scaling it up, making a second copy of our curve, and scaling it still larger. Now we just project both of them onto the body from the side so that we have two curves on surface. Next we use the extract function to turn our curves on surface into separate curve objects. Next we have to check that the starting point, shown in red when edge flags are shown, lines up with the starting point of the curves on the arm. Effect Curve Controls lets us rotate this point around. To produce one seamless surface, we've already extracted one curve from the arm, but it's probably a good idea to extract the rest of them, so that then we can skin together all the curves into one unified arm. If we make all the results visible, we can see a pretty good blend established between the arm and the torso. None of these blending techniques are perfect for every problem, which is why you need to know so many of these variations and workarounds. One of my favorite ways of making a fillet is to start with an angled cross-section and revolve it, using the same number of steps as the limb. Now you can do a deformation by surface and translate and scale the revolve until it lines up with the arm. This will make the revolve be our fillet. The Y translation should be set to put it just above the surface. Now we freeze the result, and we can either merge the fillet with the arm, or we could extract all the curves and reskin the result. This makes a pretty good seamless form. Now we'll give the arm a material and make the material red. There is still a bit of a seam to kill where the arm hits the body. We'll fix this with a 2D texture and call up a gradient pattern. This will be a UV map, and we don't need to affect the diffuse or ambient values, only the transparency. Now in texture mode, we can scale the texture down to only fit around the base of our arm. Notice the gradient it makes between the arm and the body. Now, if we match the color of the body and the arm, then with this map an imperfect fit in the shaded view can render completely seamlessly. And this brings us to the next section of the tape, which will focus on rendering. Here we have a scene rendered in the Softimage renderer that's textured using a number of different mapping techniques. Some objects in the scene are simple polygonal set pieces. Let's select the base of this bridge and recreate the process of applying maps to it. We'll start in the 2D global texture and select a cement texture map. To project it across the front of the bridge, we'll use XY projection. Now when we go into texture mode, a red box shows where the texture will be projected. To texture a large bridge, we'll go back and set it to repeat 3 times across and 2 times top to bottom. Click OK, and now the projection shows us where the repetitions will fall. If we preview the object, we'll see that the front looks pretty good, but the texture is stretching out along the parts of the object that run back with the angle of projection. There are different ways to solve this problem. One is, while we're in texture mode, simply rotate the texture in Y so that it's off-axis from the walls. This works pretty well in this case, but sometimes takes away control over the specific mapping for each wall. To make a separate map for the side walls, let's go back to Textures 2D Global and click on Next to add a new texture. We can select the same texture map again. By the way, the reused map will be loaded only once into memory during the rendering. We'll apply the map in YZ projection. Now we have a texture coming from the side. If we preview it, it looks great from the sides, but is covered over the main front surface. This is easy to fix. While we're in texture mode, we scale the texture down just a little bit so that the projection from the side doesn't quite cover the front edge. Now the base of our bridge is complete. Now let's make visible the stone arch on the underside of the bridge. It's a patch surface, B-spline in the direction in which it's curved, and linear for the direction it runs down and back. We'll give it a 2D global texture and select a stone wall texture map. First off, let's make the map darker and put some texture into the specular highlight. Now, if we left this texture in XY projection and previewed it, we would see the stones in the texture run straight across the surface with no regard for the curve of the arch. So we'll switch to UV coordinates to wrap it into the right shape, and now when we preview, the texture seems to fit the surface much better, even wrapping smoothly around to cover the underside of the bridge. To keep the stones from looking so stretched out, we'll give the map 3 repeats going around the arch and 2 going down and under. This is looking pretty good, but we'll make it respond to the lighting in the scene a little bit better by adding some roughness. And preview again. It's okay for your preview when it doesn't have anti-aliasing to start to look a little dithered like this. Your final rendering with anti-aliasing and motion blur can still come out just right. UV maps don't just follow the shape of a surface, they follow the parameterization. If we add points to this B-spline patch, we can see the UV map bunch up around the extra points. If we drag points over the surface to make it uneven, then the map will be warped as it flows along the individual U-direction curves. With NURBS, you can even end up with a surface that looks like it's evenly subdivided, but has uneven parameterization, because points keep their UV values when they're moved and other points are added. If we say Affect Reparameterization, we can set the surface to uniform for an undistorted texture. Undistorted textures are especially useful when you want to apply tiling maps that repeat smoothly across the surface. We've been relying a lot on using multiple repeats of our maps across each textured surface, This isn't something you want to do with just any image. If we took a picture that wasn't specifically processed as a tiling texture map and applied it with a number of repetitions, we would see visible seams, edges to each repetition of the map in our rendering. There are these little gadgets labeled tiling here that are supposed to help with this by flipping every other repetition of the map upside down or backwards. If we try a horizontal and vertical mirroring, it does hide the sharp edges of the repetitions, but we can still see the axes where the map runs into a horizontal or vertical reflection of itself. Generally, we want to leave the tiling gadget set to the first option so that all repetitions are upright, and use maps that are processed in a program such as Adobe Photoshop to specifically serve as seamlessly tiling maps. Here's the photograph of a brick wall that didn't tile very well. This is a good picture to make into a tiling map. It has very little perspective, since it was taken from a distance away with a telephoto lens, and very little evidence of lighting, since it was taken with the diffuse light available on a cloudy day. The key function we're going to use in making a tiling map is the filter other offset command. Offset, in its default mode, simply slides the image a specified number of pixels horizontally or vertically. When you set it to wrap, the pixels are pushed off of one edge, wrapping back around to enter the canvas from the other side. Offsetting the image to the right, in wrap mode, moves our seam to the center of the image where we can see and correct it, while giving us seamless edges. The bricks at the right edge of the frame used to be in the center of the image, and the other half of the same bricks now continue onto the left side of the image. The continuity of the left and right edges guarantees that two repetitions of this map would fit together seamlessly left to right. The same process can also be done vertically, bringing the top and bottom of the image together. We can clearly see now that the image wasn't ideally rotated or cropped for tiling. So we have to go back to our original picture and try and do a better job of aligning it. First, it seems to be slanted, so let's take the line tool and drag a line along the edge of the mortar so we can see the angle measured in the info window. The image is slanted by 1.2 degrees. So we can undo the line we drew and rotate the image 1.2 degrees counterclockwise. Now we can just crop the image along the edges of the mortar, and we're ready to try the offset filter again. That worked much better. Things are lining up really well, and all I have to do now is use the cloning tool to cover over the remaining seam in the center. We can copy any intact brick over the half bricks that are butted together, and when we finish making a seamless map, bring it back into Softimage. Now we can pick our tiling brick pattern, and it goes on a lot more smoothly. While there are no seams, we can still clearly see the redundancy in the 3 repeats of the brick pattern. But as we work towards a more complete scene, the surface will be broken up and given more variation in other ways, such as with more varied lighting. When we adjust lights to illuminate our surface less evenly and from more different angles, we get a less dead-looking surface. If we also put a little color into some of the lights and edit the texture to add some roughness, which varies the shading of the surface even more in response to illumination from different angles, and then if we also broke up the geometry itself a little, then the tiling of the map is much less noticeable. Let's jump back to our sample scene. Look at the way the flowing water eddies around the pylons. Here's a pop quiz. With what we now know about texture mapping, how do you think we made that flowing water? If you guessed that the map flowing along the surface was a UV map, you're right. To distort the flow of a UV map, all we have to do is distort the surface it's mapped onto, pulling points in the top view to stretch where we want it to speed up and compress where we want it to slow down. Now we can see in texture mode that just translating the texture in Y, which corresponds to the V offset parameter in the 2D texture dialog, gives a flowing distortion effect to the repetitions of the UV map. So when we animate the texture's V offset from one value to another, we get flowing water. To make the water distort the scene that's reflected in it, we add roughness to the texture. Roughness, more commonly known as bump mapping, will both break up the specular highlights in a surface and also distort the reflections. For greater realism, at least a small amount of bump mapping is usually helpful on any shiny surface. Another water-related effect that's happening in the scene is the impression of light being reflected off the water back up onto the walls. Now, the walls that receive this light are not reflective themselves, and radiosity is not supported in the renderer, so we have to fake the reflected light effect by projecting light up from underneath the water. If we look under the water, there are several point lights. Each point light has been set to cast a ray-traced shadow, and it has zero umbra intensity, or no brightness in the shadows. A surface above the light actually casts the shadows, and it has a 3D global texture on it. The texture is set on marble, and since all we care about are the shadows the surface casts, we don't need it to affect the color of the surface, only the transparency. Only transparent parts of the object will let the light through, showing the pattern in the shadows. To animate the texture, we choose to change translation values over time. We enter starting values for frame 1, press key, then enter other values for the last frame, and press key. Now we can have an animated texture to project into the scene. Let's start from scratch with a simple scene illuminated by a single spotlight. We can create a shadow by putting a surface in front of the light. To attach the surface so it'll stay in front of the light, we'll constrain it to the light's interest. Next, before using the direction constraint, we need to rotate the surface's center so that X is up, because constraint direction makes an object's x-axis point at another object, in this case at the light. We can also adjust the size to fit the light's beam. Now, rotating or moving the light will carry the shadow caster with it. This surface could be trimmed into a shape to cast a shadow, or could be texture mapped with any 2D or 3D textures. We'll give it a material as a shadow object so that it'll cast shadows without appearing as a surface in the rendering. Now we'll put a pattern into our shadow by applying a 2D global texture to the surface. In the texture, we'll choose a high contrast picture of a tree branch. We don't need it to affect the color, we just want to use the RGB intensity to set the transparency. Now we can preview our scene, and we see natural looking shadows being cast by the light. This technique also works in the Softimage renderer, and it's one of the few lighting effects on the computer that hasn't been overused enough to be considered a cliché yet. Since we're rendering in mental ray, we also have the option to use a light shader instead of our shadow casting object. Without the shadow casting object in the scene, we can start from the beginning by selecting the slide projector as a light shader, and then select our same tree branch map in the light shader. This is how we set it up in version 3.7. The results when we preview are very similar to what we set up before, but we still sometimes need to use the first technique to mount objects in front of a light or camera. The slide projector shader limits you to only mapping on a file and couldn't be linked to that animated procedural texture for our water, for example. Let's run through how the sample scene was rendered in layers to build the final composite. The background shows several examples of projected lights. The light beam model itself was just a transparency mapped object running through the scene. Next we have the train interior layers going by, rendered with an alpha channel for compositing, as with the exterior of the train. The MB utility added the motion blur to each of these elements. Since these renderings all came from the same scene, re-rendered with different elements hidden or deleted each time, the layers all lined up to create the final composite. Another thing you often have to isolate are your shadows. The technique I like best for this is one that works in either the Softimage renderer or Mental Ray. Select the shadow casting light and set it to a negative value, and also set the light's umbra intensity to a negative value. Now you can say OK, and you can see the negative light in the perspective window. You can also see this general grayness outside of the light, which reminds us that we still have to set the global ambience in the scene to 0. And now the rendered result will be a mask showing exactly where the shadow was cast over black. The thinner line here is just the shadow of the beveled edge of the cube. Sometimes we need to make elements that will be partially obscured by a live action element or appear to be behind part of a separately rendered element. This animated sphere will be moving through this live action shot, which I've lined up as a rotoscope wire background picture. But this column in the shot should appear in the foreground, so I've made a simple 3D model to hold the place of the column. Now in rotoscope shade mode, we can see that the column model obscures our sphere. But we want to see the column from the original live action plate, not a rendering of our dummy object. So in the dummy object's material, we'll select the alpha material shader and edit it to force the alpha channel rendered with our object to a value of 0. This means 0 opacity, so the area of our rendering will show through to the live action column when the graphics get composited by their alpha channel. A quick way to preview the results of an alpha channel based composite is to use the background picture output shader. After we've selected the shader under render options, we can edit it and choose the same image as we chose as the background in our rotoscope wire mode. Now when we render our animation, after each frame renders, the output shader composites the picture into the background based on the alpha channel. We can see how our dummy column object holds back the graphics and lets us see the original column. The interior of the train cars use many layered and blended textures. We can find an empty seat back here and go through the process of adding an extra detail to it. In Texture 2D Global, we'll see that there are already several maps on the object. We can click Next to go past each of them until we get to the undefined texture at the end, and then we need a new texture map. We could make the map in Adobe Photoshop, starting with a photograph. First we use Select Color Range to mask it out from the background. Of course the background started cleaner on the items painted in Fractal Painter than on the digitized ones. With the detail area selected, we say Select Save Selection to store the selected mask as a fourth channel, or alpha channel. This alpha channel mask is what will be used to blend our detail onto the object back in Softimage. So we select the map with the alpha channel, and when it's viewed on the material, we can see a limited preview of the way the texture will be blended with what's under it. The default blending for the map makes it opaque, so that the full rectangle of the map would be visible. When we switch our blending mode to alpha channel mask, then only the area we masked out in Photoshop is used. But now we need to adjust the values to make the map more visible, since the red color of the writing is too close to the orange material. When one of these three ambient, diffuse, and specular sliders is at 0, then the texture's influence over that attribute of the surface is turned off. So while the diffuse slider is at 0, the surface uses the diffuse color that was set in the material or in a previous texture. Once the slider is set to any non-zero value, then that color of the material is completely replaced by the color from this texture map, or could be blended according to the blending settings above. Once a slider is at a non-zero value, its value adjusts the brightness of that attribute of the texture, not the blending. We can even type in a brightness value outside the slider range to texture on a diffuse color brighter than the colors in the map. Or we could adjust it darker for more contrast, which is what we want here. We're still seeing the specular color set in the original material, but setting the specular slider to any non-zero value will replace the material specular color with the color from our map. We can say OK to this texture and go into the texture translation mode to position the map. It can be scaled, rotated, or translated into the right position. We can also go through and adjust all the individual textures with the next and previous functions in the texture menu, and see the texture nodes highlighted in the schematic window, or see and transform the texture boxes on the wireframe. With everything in place, here's a look at the small tag we've added. If we look up at the ceiling, we'll see a map with another use for its alpha channel. The ceiling has a reflective material, and the reflection is distorted by a bump map. The actual ceiling texture was created from scratch in Adobe Photoshop, with a separate image for the roughness or bump mapping stored in the alpha channel. The brighter parts of the alpha channel will be shaded as though they were higher, and the darker parts lower. The map is applied with the RGB color on the diffuse value and the map component, which routes an image to the three sliders below it, set to use the alpha. To use it as a bump map, we just choose a non-zero value for the roughness slider. If we look at a rendering, we can see that every reflection in this train is softened by some amount of roughness because there are no completely perfect mirrors. The cigarette poster applies its bump map differently. It has one map that's just the RGB color image painted in Fractal Painter. The next texture, scanned from a crumpled piece of paper, is not blended with the color values of the image, but since the map component is set on RGB, the RGB image is applied as the bump map. Like the train car ceiling, these tiles that are mapped on have an alpha channel bump map. The tiles each have a gradient running in a different direction to vary the apparent angles of the individual tiles, so they can each break up the highlights and reflection of the shiny surface, and each appear to be set into the wall separately. This wastebasket looks like it could be a complex piece of geometry, but it's actually a simple revolved surface. The first 2D global texture applied to it maps on a color pattern and also has an alpha channel applying a roughness effect to shade the metal lattice as though the lattice had thickness. The next map is a monochrome map applied only to the transparency to effectively hide the portions of the surface that will become the holes. This is the so-called clip map. It can save an enormous amount of modeling time compared to building geometry for the lattice. Here's a scene that I want to light realistically. Step 1 in any Softimage scene that you want to look good is easy. Select Atmosphere, Ambience, and set the value to 0. The only alternative to this would be to set the ambient color values for all the non-light emitting materials and textures in the scene to 0. This scene has a visible light source, the bulb in the alcove, as the key light. A so-called upstage key light, our primary light source, will be behind our subjects, casting shadows towards us. The key light will be positioned inside of the 3D model of the light bulb. The light will cast shadows, but we don't want the light bulb object to block all the light from the rest of the scene, so we make the light selective and set it to exclude the objects that it's associated with. Now we can select the light bulb object and say Light Associate, and associate it with the key light so it will not receive illumination or cast shadows in the key light. Now if we preview the scene, we see the light in position. Working in an untextured scene can be useful in setting up lights, but these materials need to be adjusted. I'll select all of the walls and make sure that they are not going to be shiny. And I'll select the light bulb itself, and then I'll give it a constant white material. Now our material is going to look a little bit better. We can see the area right around the light bulb should be much brighter, so we can add 1 or 2 more lights in the area of the key light and give them a more local fall off. Now the area right around the key light will be more appropriately blown out. Since these lights decay in a linear fashion instead of with a sharper inverse square fall off like real light, we often need to help the rendering a bit with extra local lights near the light source. By this point, the shaded view will have stopped being useful, and we have to continue doing all our tests with previews of the scene. The next step will be to add the effect of bounced light, or light that hits the walls and reflects back to softly illuminate the scene. A spotlight with a 0.2 brightness will be able to shine through the walls since it won't cast shadows. We'll put one copy into position and then duplicate it and add another one for the opposite side walls. A third copy can be adjusted to a lower brightness and used coming back up through the floor to simulate light reflected off of the floor. When you get the bounced lights balanced about right, your whole scene starts getting a softer, more natural feeling with less of the lunar landscape look that's typical of many 3D renderings. These bounced lights are not what you call fill lights in live action. These are extra computer light sources added to simulate the illumination by reflected light that occurs naturally in a real scene, but isn't otherwise simulated on a computer without radiosity. We can adjust our lights a little bit and tint them away from white, so I'll give this tungsten light a slightly warmer, yellower color. The quality of your rendering slightly improves when there's some color in your lights, and even just a little bit will help reduce banding artifacts and improve shading. Now our background light will be more boldly colored, as though colored signal lights were used in the tunnel. We want to wash the background with a cooler blue color. And we'll give this spotlight a 0 cone angle, but a spread angle of 80, which means that over the course of the cone it'll be fading off from being most intense exactly in the center point to fading all the way off by the edge of the cone. And we can see that we still need to pump some more blue in there, so we'll make a second copy of the light and give it a more intense blue, but also a smaller spread angle. Now we can also add a fill light, and we want this one to look as though it's coming from a red signal light in the tunnel. Warmer colors, especially if we choose a hot red, pop out into the foreground when seen against cooler background tones. Remember that the purity of color in this preview will be tempered and made much more subtle when we load in the materials and textures for the scene. But one last lighting option we should show is that we could select a camera shader to add a glow to our key light. We'll select the light we want it applied to, our key light, and now the only active effect we want is the halo, so we don't need the others turned on. Now there'll be a glow around the overexposed part of the image. Looking at this scene, we only perceive 3 apparent light sources, even though we used 2 lights for the key, 3 bounce lights, 2 background lights, and 2 fill lights in the scene. Now that the lighting's starting to take shape, we can take a look at the final rendering, including all the materials and textures. These were added using the same techniques as in our texturing sample scenes. If we look up close at any area from the final rendering, we can see an extra advantage to having multiple lights represent the same light source. Shadows, like the diagonal slash seen here, appear to be softened by the multiple lights, so that from a greater distance we get a sort of poor man's soft shadows in our rendering. This sample scene still has global ambience turned on. If we want this lamppost to look like a light source, we can position a point light near it, and we can give the globe at the top a constant material. Now moving the light and lamppost together lets us add shading to the buildings. But if we wanted to map illuminated windows onto a building, we wouldn't want to make the building constant like the globe, because the walls should still be getting this illumination from the lamppost. What we do is first make sure that the material doesn't have any ambient value, and we should do this for all the materials in the scene that don't have their own illumination. Now in 2D textures, we can load up the map of the lights for the building. Now to just map the luminosity of the windows onto the building, we want this map to only affect the ambient or self-illuminating part of the model. Some programs separately label this kind of mapping as luminosity or incandescence mapping. Now the value of the ambient slider, which is being multiplied by the scene's global ambience setting, determines how much the map adds to the illumination of the building. The black pixels of the map don't add anything to the illumination of the surface, so they effectively mask themselves out. If we preview, we can see that the windows are self-illuminating, but the sides of the building are still shaded by the light from the lamp. Another important kind of map is a specularity map, which can determine which parts of a surface are shiny or have brighter specular highlights. We can look at this character's texture assignment, and the first map is applied to the diffuse color. Next, another map is used specifically as a specularity map. The specularity slider is up at a value of 0.7, while the diffuse and ambient sliders are both at 0. This map gets brighter in the places that should be shiniest on the character, and gets darker or black in the places where we don't want specular highlights. If we preview him, we can see the highlights on his nose from the bright part of the specularity map, but not so much on his cheeks or chin. Specularity mapping works better than painting these highlights directly into the color map, because these highlights can travel across the face when the head is seen from different angles. We'll come back to this head in the last section to talk about how we animate it. Shape animation is one of Softimage's most powerful and versatile types of deformation. One of the easiest ways to set up a shape animation is with the Save Key Object Shape function. We can store one shape for this object at frame 1, then go to another frame and modify the positions of any of the points in the model. Now we save this as another key shape. When a shape animation is created, 2 types of data are being stored: your shapes themselves and the F-curves that control them. A shape is information storing a position for every point in the object relative to the object's center. Changes made at the object level, such as scaling or translating the model, are not recorded by shape animation. You can see all the individual shapes that are linked to a shape-animated object by looking at your shape list for the object. Clicking on one of the shapes will make the object show you that shape. Shapes stored while the object was scaled differently are still redundant. The shape F-curve tells the object which shape number it should be using at any given frame. When it has a value of 0, then we see shape 0 at that frame. When its value is 1, we see shape 1, and so on. Shape Select Key Shaped will prompt you to click on another object to get the new shape from. This way, you could make several different versions of an object ahead of time that you wanted to use as target shapes for the same animated model. The models all need to have the same number of points and use the same type of geometry. Usually, you'll start with duplicates of the same original model. When you click on a target model, your shape-animated object immediately takes on that model's shape, and that shape is added to the shape list. Using a shape F-curve to control your animation, you don't have random access to sequencing your shapes. To blend from shape 5 back to shape 1, for example, you must pass through all the other shapes as the curve slopes downwards. To even make a loop, you'd have to add an extra shape that duplicated the first one to the end, but then we'd be wasting memory with redundant data. Continuing to expand the shaped list like this through a long animation would eventually crash even the largest machine. To fix these problems, we can use the most powerful shape interpolation mode, weight interpolation. Here the shape F-curve does not matter at all. Instead, a set of shape weights F-curves, one for each shape, are used. To make a looping animation more efficiently, we could now edit the curve of the first shape so that it comes back up to 1 at the end of the animation. We can also combine any shapes we want at any frame. For example, I could make a combination of shape 2 and shape 4 by bringing shape 2 back up to a value of 1 during the time when shape 4 also has a value of 1. Now we're getting an averaging of the two shapes, so the shapes are each blended at half their intensity. In the object shape list, we can change the blending mode, labeled animation, to additive. In additive mode, I can combine them both at their full intensity. Blending in or out my shape 2 now has no effect on the dent created by shape 4. I can even give a shape a negative weight, so that now a dent that was pulled inwards in the shape swells outwards in our animation. It was okay for me to demonstrate Select Key Shape by laying out all the target shapes in different places on the screen, because the shapes in the shape list only record the position of each point relative to the object's center. In a real production, however, you probably will need to move each object center as a part of the modeling process, so when I model a set of facial key poses, I leave them in the same position in space and hide the ones I don't want to see. This way, the center's location for each model can easily be frozen to the same coordinates, and it's easier to compare models. Then, before beginning your animation, you just go through and can use the schematic window to select key shapes for each of the poses in your library. After they're assigned as shapes in your shape list, you don't need the original model of each pose in the scene anymore. Although, of course, it's a good idea to keep a backup copy of these models somewhere for when you have to reassign them. Everything starts with a neutral pose, the basic expression from which the others are derived. This is the one pose that you model first and then duplicate and modify to make the other poses. This is also the version of the model you should use when assigning a global envelope to the character before selecting any target shapes. For the best control over facial animation, the shapes themselves should be modeled by modifying only one specific area or attribute of the neutral pose in each model. If we did need both eyebrows to raise at once, for example, we could still raise the shape weights F-curves of both of these poses in unison, but this way we have the control to vary them asymmetrically. The names of each of your models are lost when they're assigned as shapes, so they're now called shape 1, shape 2, and so on. As you go through your animation editing the shape weights F-curves, you might want to keep a list on paper of what shape number is used for each pose. Another thing that needs to be worked out on paper is your lip sync information. You should use your choice of audio utility to scrub through the soundtrack and note which phoneme or spoken sound is being made at each frame. Then, with an exposure sheet written out on paper, you can go into Softimage and pick mouth poses that seem appropriate at each frame. Another way to control your shape weights is to set up nulls and give them each the name of one of your key poses. I'll call this one Grin. Then we can write an expression on our shape animated object that says that shape weight number 1, which is the grin, is set to equal a value taken from this null. I'll use the X translation as the value so that we can slide the nulls horizontally to vary the shapes. Now when we translate the grin null horizontally, we see the grin shape update, and we can even slide it to the left of the axis for a negative weight of a grin, which of course looks sad. You'll need to write an expression like this to link each shape weight to each null slider. Animation can be created by keyframing the explicit translation of the nulls or by editing their F-curves. If you multi-select some sliders and then select their F-curves, then you have names on the screen for each of the poses, making the process slightly easier. For more complex characters, facial animation can still be a very involved process because a finished line of dialogue can take hundreds of keyframes for the different facial features. We'll finish the program with a look at one brief shot chosen because you now can recognize all the modeling, texturing, and animation techniques that went into it.
So I thought about it for a moment, and then I said, okay.